Hi, I'm Talha, and I'm presenting our paper, Differentiable Composite Neural Sign Distance Fields for Robot Navigation in Dynamic Indoor Environments. Indoor navigation entails inferring collision costs for static and dynamic components of the environment in real time and usually in clutter to guide downstream planners. It becomes particularly challenging when we limit our setup to only a robot mounted visual sensor. As challenging as the task may be, this opens up a broad range of applications including home assistance and warehouse management. Previous works have tackled the problem in different contexts. We focus on building upon the rich framework of sign distance fields. Real sign distance fields have recently emerged as a powerful paradigm for modeling with real time inference, arbitrary query resolutions, and automatic differentiation, all attributes that make it particularly favorable for gradient based trajectory optimization. However, real sign distance fields require training, usually with full scene information. This is slow and impractical. They're also tedious to update with a continuously changing scene. Additionally, indoor navigation approaches usually assume access to a known trajectory of moving obstacles and access to multiple sensors positioned across the workspace. These assumptions limit the practical feasibility of such approaches. Towards these challenges, we present a dual mode framework of neural SDFs that bridges dynamic scene understanding with trajectory optimization. Dual mode refers to the robot SDF and the scene SDF pipelines, each complementing each other and working in tandem to optimize the trade off between fast trajectory updates and accurate shape modeling. Here we show these two pipelines in action across time steps where the object position changes. From an observation of the scene, we can either proceed with the robot SDF pipeline or with the scene SDF pipeline. The scene SDF pipeline infers the visible scene's SDF using prior information. The pipeline segments object point clouds from background and infers their workspace to SDF domain mappings. The information is combined via a simple min operation and used in trajectory optimization. Note that our composition preserves differentiability. However, this process is compute intensive and redundant to perform at each time step as the scene does not drastically change in short durations. Hence, we should make the most out of each output from the scene SDF pipeline and amortize our compute and time costs. Here we present the robot SDF pipeline, which directly queries the robot body's SDF on partial point clouds extracted from visible obstacles. Doing so is fast, requires minimal working assumptions, and serves as a check for when the scene SDF pipeline needs to be invoked. The queried SDF costs and gradients then guide trajectory optimization. Here's a scenario demonstrating the two pipelines working hand in hand, where the robot SDF pipeline gets stuck in a local minima and then calls the scene SDF pipeline to infer scene information to generate a better trajectory. The scene SDF pipeline then hands over the operation back to the robot SDF pipeline to continue. We benchmark our method and its components with a method which uses an efficient proxy of the SDF called ego trajopt and the classical DWA. To give some context of the environment complexity, we use an IRT star planner with full scene information. Note that IRT star is both time consuming when ran repeatedly after every change in the environment and less successful as the clutter in the environment increases. DWA is fast as it only considers the robot's locality while planning, but its evaluation function is known to be sensitive to dynamic obstacles. Our method avoids these issues and gives the highest success rate with a competitive planning time. Here we deploy our method to a turtle bot navigating in a real-world indoor scenario. The robot plans an initial trajectory to the goal area at the bottom of the screen. Then we place a briefcase in the robot's path, after which it replans to avoid the briefcase and reaches the goal state. In summary, we propose a novel framework of neural SDFs for robot navigation using only an onboard sensor. Our method comprises of a robot SDF pipeline that directly queries the robot body's SDF to guide trajectory optimization, and a scene SDF pipeline that combines visible scene elements with prior information to give more accurate shape information. We combine the two pipelines to give the best of both worlds and achieve a pragmatic approach to motion planning in indoor scenarios. Thank you. Please visit the project website for more details.